Hello everyone, how are you? And good morning. Okay, so this workshop is going to be the very first workshop on the course list, okay, on the curriculum list, and this workshop will give you the important knowledge about applying the CFD and learning the CFD softwares, and then comparing your results with the analytical data, and also we will go into the very deep about the meshing, their effect on the results, validation, everything will be covered here, okay. This is going to be your first workshop and you should learn it very well. Okay, now let me briefly tell you that what is going to be here. So one is like a picture of the mesh, that is hexa meshing. We will cover different type of meshings here. And this is the result of the velocity profile, radial velocity profile with the 3 to 4 meshes. Okay, 3 meshes and one is analytical data. And you can see that the tetra meshing, not because of the having the less number of cells, but because the core mesh inside the volume has a less elements. We don't have the much control there. We can see that the data is not very good in the main core region, okay, but on the boundary layer on the sides it's okay. These are pressure contours. This is the picture of the circular cylinder and the governing equation of the fluid flow in the circular cylinder. That is, the convective terms are balanced by the pressure drop. Okay, so this is the whole contents that we are going to be learning in this workshop. So these are a lot of things that we will be learning. And one thing that I want to clarify that right now we are going to solve this case as a 3D, but I will be giving you the idea that if I take the only a 90-degree sector or the 1/4 of the 360 degrees, and if I get the only a single plane, okay, single plane like a symmetric case, so what will happen with the results? So that we will see, okay, we will see that thing also. And so there are a lot of things that we are going to cover here. So problem description is that we are going to solve the laminar flow in circular pipe at Reynolds number 100, and because the less than 2300, so flow is laminar, and if the Reynolds number is greater than 4000, then the flow is turbulent. In between 2300 and 4000, the flow is transitional. So it's a theoretical analysis. So I told you this thing that okay, this is some animations that shows you that initially the flow is laminar, like a laminar, and then the flow goes with the transition, and then flow becomes the turbulent fully here, okay. And one more thing is that you should be very much clear about that thing, that it's not required that the Reynolds number should be this value. If the disturbance and when Reynolds number is low, the flow can become turbulent. So disturbance is another factor, okay. So without disturbance, Reynolds number is the important parameter. So you can see here the whether flow is turbulent or not. So here you can see that initially the flow is laminar. Once it goes through sudden expansion here, so the velocity and other things didn't change, but because of the disturbance here, the flow becomes the turbulent from laminar flow. And same goes with the flame here. Okay, so we can define Reynolds number as the ratio of inertial forces to the viscous forces. So now let's drive the formula that you see, usually speaking, the rho v L upon mu. This is the density, this is the viscosity, this is the velocity, and this is the characteristics length. Means this is the length that is going to influence the flow, okay. So this can be the diameter in case of pipe, this can be the chord length, this can be the like a step height. So it is like a dimension that is going to govern the flow, okay. That dimension should be put here, okay. Okay, so now the inertial force, like we know about the Newton's second law, is equal to mass into acceleration, and density is given by the mass upon volume, right? So from here I can write it down that the mass will be equal to density into volume. So I can put it over here, and I get inertial force as the density into volume into velocity, acceleration, velocity per unit time, so velocity upon time. And so from here we have the density, volume upon time, and velocity. And volume upon time is the Q, volume flow rate. Okay, it's a volume flow rate which is equal to the area into the velocity. Area into the velocity. So now we have the density into area into velocity into velocity. So velocity into velocity is equal to velocity square. And this is like rho a v square. Rho a v square. Okay. So inertial force, we can write it down in terms of the velocity and density and the area. And we know that the viscous force is the shear stress into the area because the shear stress is equal to force upon area. This is same like the pressure, but there's difference in the like how the effect is there. Okay. So now I can write it down. The viscous force is the shear stress into area, and we know that shear stress is given by definitely minus sign will be there to give you the positive value of the shear stress. So, but the formula is that it's a viscosity and it's a laminar viscosity, and du by dy. This is a normal like gradient. So, if the velocity profile is this one, this is the velocity profile along the y direction, du by dy. This is the actual velocity, but we are getting the gradient along the y-axis. So from here we can write it down the mu and du by dy as like if you are like integrate it with the whole length of the geometry. This will becomes the u becomes the small u becomes the v and the y becomes the length and into area. Okay. Into area. So we have this formula. Now I can put these values into the Reynolds number formula. Inertial force, which is here, and shear viscous force or shear force, which is over here. So rho a v square mu v upon L into area. So I can cancel out the area. I can cancel out the 1v from denominator and 1v, and this is only 1v in the denominator and the v square is there, so 1v will be cancelled out. And finally we get the rho v and L will go on in the numerator. So this is a rho v L upon mu. Okay. So this is the traditional formula we have for the Reynolds number. And for pipe flow, the important characteristic length is the diameter. So that's why the Reynolds number would be the rho v d upon mu. Okay. So in case of the laminar flow, the Reynolds number is less than 2300 for the internal flows. And so there is maybe there are some small disturbances are there that will be damped out quickly. And then we have some disturbances, but they are in the different locations. And sometimes they continue, sometimes they are like are damped. So this will like intermittent burst of the turbulence will be going into here and there. Okay. And if the disturbance is continuous, then we call the flow as turbulent. So in terms of Reynolds number, when the Reynolds number is more than 4000, the flow becomes turbulent for internal flows. And between 2300 and 4000, the flow is transitional, like that. Okay, for external flows, the situation is different. So for external flows along a surface, Reynolds number is greater than 5 lakhs. So flow is called the turbulent. But the more particular definition is that from 1 in 10 power 5 to 3 in 10 power 6, the flow is transitional, and greater than the 3 in 10 power 6 flow is turbulent. Okay, and less than this value flow is laminar. I will show you that thing also. And when the Reynolds number around the obstacle, like a circular cylinder or a building, in that case, the Reynolds number is more than 20,000, the flow becomes turbulent. Okay, and other things like a free stream turbulence, I told you this thing. Surface conditions, blowing suction, other disturbances may cause transition from laminar turbulent flow very early. Okay, and here you can see this is a simulation of with the help of the DNS or LES, and you can see a lot of structures, turbulent structures over here on the aircraft body. And so how the flow like on a flat plate or any surface, that if you zoom that surface, that becomes the flat plate. So initially the boundary layer will be laminar, then it will have the transition to the like a transition region is there, and then after transition the flow will transit from the laminar to turbulent. And turbulent flow will have the multiple layers. One is the viscous sublayer that will behave like a laminar flow. Okay, so here the laminar stresses are important. Okay, buffer layer is the layer where the turbulent stresses and laminar stresses both are important. There's overlap layer and then turbulent layer. Okay, Okay, now if I take example of the flow around a sphere or circular cylinder, so here you can see when the Reynolds number is less than 5, okay, there is like a flow is fully attached with the geometry, no separation there, okay. And as the Reynolds number increases from 5 to the 40, sometimes maybe a lower range is 15 to 40, maybe 10 to 50, 10 to 40, so it varies, okay, but like generally speaking 5 to 40. So there will be like a fixed pair of vortices will appear here, okay. And then from the 40 to 90 and 90 to the 150, there are the two regimes in there, okay. So there is a vortex state is a laminar, okay. This is one thing that this is a laminar flow in the vortex state, and periodicity governed in the low RA range by the wake instability, and periodicity governed in the higher Reynolds number by the vortex shedding, okay. So it's a in this range the wake instability is actually is making the periodicity of the like flow, and in the high range up to 150 this is governed by the vortex shedding. So whenever we are solving the flow for vortex shedding, laminar vortex shedding, I usually keep the Reynolds number from 100 to the 150, and that you might see in the course contents when we solve the circular cylinder and a steady flow on the circular cylinder. And when Reynolds number, again there are two values here, Reynolds number 150 to 300, the transition range turbulence in the vortex. So flow will be transiting to the to turbulent flow in the vortex. And but from Reynolds number 300 to the 3 to 10 power 5, the vortex stays fully turbulent, okay, here. But the flow in the like here, flow is still laminar, okay, flow is still laminar. But from here to here, the flow becomes the turbulent in the wake region. And from 3 to 10 power 5 to 3 into 10 power 6, the laminar boundary layer has undergone turbulent transition. Now the boundary layer here is also turbulent, and the wake region is narrower. You will not observe the any vortex over there, okay. It's a narrow, size is also decreased, and it's disorganized, and the vortex state is apparent definitely. No vortex state is apparent here, okay. So flow is disturbed here and going without any vortex shedding. And once the Reynolds number is greater than the 3 into 10 power 6, we will have the turbulent vortex state and turbulent boundary layer flow. So it's like you can match it with this flow over here, okay. You can match it with this flow. So but the vortex state will be having the less width than the turbulent flow. Okay, so now we will discuss about the flows in the pipe. Okay, flows in the pipe. Okay, so here the entrance region is the region of the pipe that where the flow is developing, means that the flow will be changing its properties, changing its velocity, pressure, everything, and it will be non-linear. And when the flow becomes a fully developing flow, means that when the flow is fully developed, it means that when the velocity does not change along the length, it means that the du by dx is equal to 0. So at the one point and the second point, this is u1, let's say, this is u2. So they both are equal. So it means that the u1 or u2 minus u1 is equal to 0, and therefore the du by dx is equal to 0. And once the flow becomes fully developed, and that region the velocity profile is well established, and that is the parabolic for the laminar pipe flow. And secondly, the pressure gradient is also constant. It's a linear and it's a constant value, means that it is changing with the linearly with the length. And in the case of the any pipe flow, the shear stress will be maximum at the wall, and the velocity will be 0 at the wall, and velocity will be maximum at the center. Okay, now we are going to drive that the velocity is the only function of radial direction when the flow becomes the fully developed. Okay. Okay, here we have the equation in the cylindrical system, where we have the r component, theta component, and we have the axial component. Okay. So as we know that the relative velocity is not present there, it's only axial velocity. It means that although the derivative with respect to r is not 0, but the ur is 0, that's why this term is 0. And similarly, u theta is also 0. It means that second term also 0. This implies that the partial u by partial z is equal to 0. And this implies that the ux, we are talking about when the flow is fully developed, okay? It means that the gradient is 0. It means that it's not a function of the acceleration. So it implies that the ux is a function of the relative direction, because it cannot be the function of the anything at all. So it's not a function of z direction, then it is a function of it is changing in the r direction, okay? Okay, so these are the equation. Actually, these equations, governing equations for the any flow, and these are in the Cartesian coordinate system, means x, y, z. So first term here on the left side is a total derivative. So first is the term that is the transient velocity term, and the second term, like these three values, they are the convective term. Here's the pressure gradient, and this is the stress term. These are the normal stresses. And this one, the one is the normal stress and two are the shear stresses. But because the shear stresses are important in the z direction, it is 0 actually. So it is only changing along the y direction. It's only changing along the y direction. Okay, it's only changing along the y direction. Okay, in the y component, and actually it's changing in the both directions. So it is going to be changing in the z and y both. Okay, because that will be along the radial direction, because the radius will contain these both terms. Okay, so only axial term will be 0. In the y component, we have the u are replaced with the v, and everything else is exactly same. Okay, so only change is that the v is there, and z component w is there. Now this equation system can be changed into the cylindrical coordinate system. You can see the derivation in some good books, and here we have the equations, and we can drive them very easily actually. In spherical coordinate system, this is slightly difficult or complex, but in the cylindrical system, it's much easier. You have to transform the variables, or there are some other methods also. So these are the terms here, and you can see there's a one extra term that is present here as well, and not in the axial component. Okay. Now, if I go through the r component, and what we know that the u theta and u are 0, because the only velocity is along axial direction, and secondly the axial direction gradients along the r and along the z, along the r and along the theta, they are also equal to the 0. Okay, there's slight mistake here. It should be the x here, axial direction should be there, and theta also, but not the radian. So x or z, whatever you take, is axial direction. So you know that in the first two equations, r and theta component, the ur and the u theta are 0. That's why these all terms are 0. Okay, that's why these all terms are 0. And this means that the pressure gradient is not there in the r direction, and there's no pressure gradient along theta direction, and this implies that the pressure gradient will only be along the axial direction. Now take the axial component. In the axial component, the ux, because the steady state of the ux by delta t will be 0, and second component, the ur is 0, and secondly, either you take the ux or you take the uz. So both are axial. Actually, we are talking about axial. So they are ur 0, and secondly the partial u by partial r x, they are also 0. But so here this term is not 0, but ur 0. That's why this term becomes 0. And here the partial u by partial theta is 0. This term also 0. There is no gravity or body force term is there. Pressure gradient is there, and that's along the x direction. Okay, and in the two components, the variation of the ux with respect to theta is 0, and same is the case with along the x direction. Okay, so only component we are now having is the pressure gradient, and second is the the shear stress. So you can put them in this way, and then simplify and take the pressure term on the right hand side. This becomes the positive term. And now because this is only like a single term, so we can change the partial derivatives to the simple derivatives. Okay, so dp by dx is equal to mu upon r dr by dr r dux by the dr. And the boundary conditions will be, for this case, is that at the r is equal to r, the capital R, that is on the boundary of the cylinder, at this point the ux is equal to 0. Okay, and at the r0 means center line, the velocity is maximum, but the gradient, you can see this is straight gradient, like a zero gradient here. So pressure velocity gradient is 0 on this point. So these are two boundary conditions that will be used for solving the this differential equation to get the particular solution. Okay, now we talk about the shear stress at the wall. So just leave this thing for a time being. Okay, here take one element from the pipe, and this element is now over here. So on the front side, the area would be the pi r square, and the pressure is P. So if you multiply area with the pressure, you get the force, pressure force. And on the second side, on the right hand side, the pressure will increase by the small quantity dp. So this will becomes the P plus dp, area will remain same, pi r square. And the second thing is that on the sides, like on the periphery of the circular cylinder, we have the shear stress. That's a maximum on the wall, but direction is opposite to the flow. Why? Because it will give the resistance to the flow. Okay, that's why you put the negative sign or the opposite sign. And here the area would be equal to how much? This will be the 2 pi r. 2 pi r. What is 2 pi r? 2 pi r is the circumference. Okay, 2 pi r is the circumference, which is over here. So on the both sides, this will be circumference, like this will be like this. Okay, it's a circular cylinder, and this region is the dx. This region is the dx. So now if I multiply, this will be rectangle. If I open it up, so this will be the 2 pi r into dx into the wall shear stress. And if you make the summation of the forces, so put the negative sign with the opposite direction and positive sign with the direction going towards the flow direction. So we have the pi r square positive minus pi r square into P plus dp negative, and the 2 pi r dx and tau wall as a negative sign. So simplify, this pressure term and this pressure term will cancel out. We get the minus pi r square dp and the 2 pi r dx and tau wall. So we can cancel out the common terms like a pi 1 r, and finally we get the r and dp. And this term, if you take on the right hand side, this becomes the plus 2 dx tau wall. And from here I can write down the dp by dx is equal to minus 2, because the minus sign is here, minus 2 upon r tau wall. And now we can, this is only for a small change. So this is a small change in the dx, and the small change in pressure is the dp. For the whole pipe, this will be, length will be the L, dx will change to length, and the dp will be the delta P. Okay, the pressure change across or pressure drop across the whole pipe. So we can change the dp by dx with the delta P by L. And the difference here is that when you talk about the dp is actually is equal to P2 minus P1. Okay, but delta P is the P1 minus P2. Is the P1 minus P2. So it means that the dp is equal to minus delta P. So put this term over here with the minus delta P, minus sign will cancel out, and we will get the dp by L is equal to 2 by r into tau wall shear stress. So I can write it down, delta P, or the pressure drop along the pipe length, is equal to 2L by r into tau wall. And I can change the radius to the diameter by this formula. The diameter is equal to 2r, r is equal to d by 2, and this becomes the 4L by d tau wall. So this is the formula. And this means that if I know the pressure drop, I can find out the wall shear stress. If I know the wall shear stress, I can find out the delta P, pressure drop. The length and diameter of the pipe, they will remain the constant, okay, for that particular design. Okay, so now here we have the a same equation I have written here, this dp by dx minus 2 by r top wall. So it means that from this equation we can say that, okay, so as we can see that the wall shear stress, okay, just take a look here, is the u by du by dr, okay. Now this is a velocity profile. Actually, this is defining the velocity profile at the different locations. Now when the flow becomes fully developed, so this velocity profile is not changing, okay. It means that the du by dr is also not changing. So it means that the wall shear stress will also be the constant, because at the wall, if I put the y is equal to 0 or r is equal to r, so at this point, because du by dr will remain, this gradient will remain same, because du by velocity is not changing from one point to second point. So this means that the wall shear stress will be constant, and this means that the dp by dx also is a constant. So from this we can infer that the pressure gradient in the fully developed flow will be the constant value, means that the pressure drop will be like a constant along the unit length of the pipe, okay. So the negative sign in the pressure slope shows that pressure is dropping along the pipe length, very much clear. This also makes the value of wall shear stress positive, okay. Velocity gradient at the wall also has a negative slope, because the slope will be like this. And it means that this is a minus sign here. So wall shear stress actually, because the gradient is negative, so wall shear stress becomes a positive, okay. This will be a negative value. And shear stress at the, so this is drawn here, let me show you that the shear stress at the center will be 0, and it will be maximum on the wall, on the both, like this is the circular cylinder, so on the around the whole circumference. Okay, now discuss about the velocity profile. Here we have taken the governing equation of the flow in the pipe, and so just rearrange the above equation and we get this form, and simply integrate with respect to the r. So this d and integration sign will cancel out, and this term will be remain as it is, okay. And on this side, on the left hand side, the r will be r square upon 2 plus c1, and just take a look on this picture, the same picture we have discussed earlier. So r is 0 at the center line, and r is a capital R on the pipe wall, and x and y directions are set in this way. They are on the on the center line, and we have the maximum velocity on the center, and we have the du by dr 0, and the shear stresses are maximum on the walls and 0 on the center. Okay. So with these boundary conditions, now you have to solve them one by one, okay. So now put these first boundary condition, that r is 0, du by dr is equal to 0. So from here, this becomes the this term, okay. So 0 plus c1 is equal to 0, so c1 is equal to 0, okay. So equation 1 becomes the same. Equation 1 becomes same because the c1 is 0. Now again you have to integrate. So you have to rearrange, and this r will be on the left hand side. So divide by the r, it become r, and this is du. And if you integrate du, this becomes u, and we have the c1 here. Again, we use the second boundary condition, and from here we get the c1 is equal to minus 1 upon 4 mu dp by dx r square. This is very important term here, okay. Now you have to put in the equation number 2, and you get the velocity profile u is equal to minus r square upon 4 mu and dp by dx, and 1 minus r square upon r. So this is the parabolic velocity profile looking at the this term here. And this term is very important. We will discuss this term, and we will convert this term into the meaningful values, okay. Okay, so now the same equation is here. And at the r equal to 0, we know that the velocity is maximum, okay. So I can change the r, put the r0, this becomes the 1, and this becomes the u maximum, and u maximum is equal to minus r square upon 4 mu and dp by dx, okay. Now I will go through the simple derivation for finding out the value of the u average. So we know that the volume flow rate is equal to area into velocity, okay. Now take the very small element along the radius with the thickness dr, radius r, okay, because r is varying from 0 to the capital R. So in between them, this is r. And this is like a 3D picture here. I think you can feel the idea that we have like a tube here, okay, concentric tube where the flow is going. This is the small element there, okay. Okay, so here the area is in the meter square, V is the velocity, that is a meter per second, and Q is the volume flow rate, which is a meter cube per second. And now we know that the area of the pipe is equal to pi r square, but the area of this small element is equal to the, if we open up this, become one side becomes the our rectangle 2 pi r circumference, and the second side becomes the dr. So this is equal to the 2 pi r into dr, and this is the d actually, this is the dA. So now I can solve the equation for the V average. This becomes the Q upon A, and I can write down the Q this 1 upon A, and I can integrate the dQ from 0 to R to get the flow rate in the whole pipe, not in the one element but the whole pipe. And I can write it down like a UR into dr, okay, UR into dr. So from the Q, dq is equal to the UR into the dA. This V becomes a UR, velocity with respect to the R, changing with the R function. And here just so I can find out that the from here, this is the equation for the U average, and UR we know already, this term is here. So put this term in the integration and integrate it. So this takes some steps, but it's very simple. And simplify and integrate. So what you get is that after putting the limits 0 and the R, so this becomes the U average is equal to minus 1 upon 2 mu dP by dx R square upon 4. So now write it down over here. Write it down over here. This is the R square upon 8 mu 2 into 4 minus sign and dP by dx. And from here I can take out the common as a 1 upon 2 minus R square upon 4 mu dP by dx. And you know that minus R square upon 4 mu dP by dx is the U maximum. So I can write it down, the U average is equal to 1 upon 2 U maximum, or U maximum is equal to twice the U average. Okay, this is how this equation is derived. Okay, now put this value in the equation. So I can write it down as the U maximum 1 minus R square upon R square, the velocity profile, R in terms of U average, which is equal to twice the U average 1 minus R square upon R square. Okay. Second method of the velocity profile is from the equation of the dP by dx with the tau wall. So tau wall is the velocity velocity gradient is there, and then put the velocity gradient into the equation, solve it, and you get the same formula. And again manipulate the equation, and you get the equation for the U average, for the U maximum, and you can find out the UR in terms of U maximum and the U average. Okay, just a short note before we go into our main equation. The coefficient of friction is that wall shear is divided by the 1 upon 2 rho V square. Okay, U here, U is for external flow is a U infinity. For the pipe flow, this will be the U average. Okay. Okay, now the pressure drop. Okay, so we know the equation about the U average, which is equal to minus R square upon 4 mu, 8 mu, and dP by dx. So if I change the dP with the delta P, this becomes a minus delta P. So minus sign will cancel out, and we get delta P from here is equal to 8 mu L U average divided by the R square. Okay, and I can change the R to diameter. This will becomes a diameter square upon 4. So I get the dP is equal to 32 mu L U average upon D square. This is the equation you actually see in the books. Okay. Okay, now the friction factor and the coefficient of friction. Okay, so actually the fanning friction factor CF. Okay, so this is these are both different terms are there. Okay, so it's a known as the Darcy-Weisbach friction of Moody friction, and it's a 4 times larger than the fanning friction factor CF. Okay. So please keep this in mind that this F is 4 times the coefficient of the friction. Okay, CF. This CF actually is from the wall shear stress, and this is equal to the wall shear stress divided by 1 upon 2 rho into U average square. Okay, but the friction factor or Darcy friction factor actually is given by this term. this given by this term. We will drive this one also. And in laminar pipe flow, this is equal to 64 mu upon rho v d average. This is actually a Reynolds number. This becomes a 64 upon Re. Okay. So in the case of the laminar flow, we are actually here. Okay, we are here. For transitional flow, we are here, and for the turbulent flow, we are here. Okay. So the delta P, we know the equation we drive just now here. So from here, what I'm doing is that I'm just manipulating. So what I'm manipulating here, I'm multiplying divided by the 2. Okay. And then I'm multiplying and divided by the U average. You can see here, I have taken the L by D square and mu separately. And so this becomes U average square and divided by the U average here. So now take this term out, 64, and the mu and the V into U average D. So these terms separately over here. Okay, this is, we know this is a F, and into L by D, and into the rho U average square upon 2. So delta P also can be written as the F into L by D into rho U average square upon 2, upon the 2. Okay. Now, how this term is actually is defined, delta P is, we know that this is equal to this term. Okay. So what we are writing here is that we are writing the delta P in terms of the friction factor and L by D and this term. Okay. So if you compare this term and this term, these both terms, if you compare them and simplify, you will find out that the wall shear stress at times into divided by the rho V square. This term is a friction factor actually. Okay, this term is the friction factor. So if you want, we can also drive that equation as well. We can drive this equation as well. So let me do it. Okay. Okay, so to drive this equation, number one thing is that one is the definition. Okay, so there is no confusion about this thing. That is the, so it is coming from the definition. Okay, so actually the definition is for the CF, and this is equal to the wall shear stress divided by the 1 upon 2 rho V square. So this can be the average velocity or just U. Everything is the same. Okay, so we understand that this is, we are talking about the average velocity. Okay, now this term actually, the 8 is important thing, and that I told you that we will prove this thing that the F is equal to 4 times CF. So now this thing comes from that formula. Okay, now I'm just trying to fill in the gap that from here why we have this term here. Okay, so you know that the wall shear stress is equal to minus mu du by dx, du by dy, or du by dr. Okay, at the r is equal to r. So we know that the u is equal to ur is equal to the twice the u average into 1 minus r square upon r square. So take derivative and put the r is equal to r. This becomes the minus mu, and this becomes the 2u average into minus 1 upon r. Okay, simplify, put the r is equal to r, so 1 r will be, this will be minus 2r, so 1 r will be cancelled out, and we get the 2 upon this 2 is here now, so 2 u average and minus 1 upon r. So minus sign will cancel out, and we get the value as the 2 mu u average upon r. And if I change the r to the diameter, this becomes the like a 4 here, and the u average divided by d. Okay. Okay, so now you know that the wall shear stress is equal to the 4 times the mu and u average upon d. Okay, so now from this term, the delta P 32 mu L u average divided by the d square. Okay, so take this term as 8 into 4, and mu, okay, and the U average upon the D, and so 1L is remaining there and upon divided by the D. Okay, so and this term 4 mu du average upon D is equal to the wall shear stress, okay, and L by D. Okay, now you have to multiply uh, by the rho U average square upon the rho U average square, okay. So I can write it down as the 8 wall shear stress and divided by the rho V average square and into L by D into rho U average square. So this term is the F and this is the L by D and this is the rho U average square. So from here we know this term and we know that the F is 4 times CF that we will prove, and from there we can find out that the F is equal to the 8 times, because there is a 1 upon 2 rho V square, the 1 2 goes on the upper side, and F is equal to the 4 times CF, and the CF is like a tall wall, a wall shear stress divided by 1 upon 2 rho V square. So that's why this comes from this fact. Okay. Okay. Now, as far as the function between these two terms are concerned, CF and the F. So CF we know that is a wall shear divided by 1 upon 2 rho V square, and the wall shear stress, as I told you, this is equal to the 4 mu. That derivation also given here. So 4 mu upon R U average square. And from here you can find it out that this is equal to the, if you cancel out the terms, common terms, this is 8 mu divided by rho V average square upon into R, okay. And then I can change the R to the D, so this becomes 8 into 2 mu upon rho U average into D, and this is actually a Reynolds number, 1 upon Reynolds number. So from here we can write down the CF is equal to 16 upon R. And the F is given by the 64 upon R, okay. That is slope of the that graph, and that graph is known experimentally, okay, and empirically we have in our books. And from here I can write it down as a 4 into 16 upon R, so I can write down that the F is equal to 4 into CF, okay. Okay, now we start with the problem, and first I will go through the solution, analytical solution, and then we go through the CFD, okay. So the theoretical part ends here, and now the actual part of our particular problem starts here. We are starting with the class, and now I will start with the geometry making and then the mesh, and then everything is there. But before that I want to develop the problem. So for our case, we are given that Reynolds number is equal to the 100, okay. Okay, so first we will get some values. Okay, so for the pipe of the length equal to 40 meters, so I will discuss that thing, what is the going to dimension of the pipe. So if I take the length is equal to 40 meters, and I put into this same formula 32 mu is taken as a 0.01 mentioned here, and diameter is the 1, and velocity average is the 1 meter per second. So this is the pressure drop along the pipe is 12.8 Pascal. But as I told you that actually the some portion that is called entrance region or developing flow region, that region will be not considered, because these all equations which we derived here, they are based on the assumption that the flow is fully developed. It means that we have to take the length that is in the region when the flow is fully developed. So for that scenario, I will be taking the 30 meters. Okay, so in that case, delta P will be 9.6 pascals. Now this value actually will be more closer to CFD results, because the CFD results, if I compare them, they will be based on because if I compare theory with that thing, then this should be the length where I am going to compare our CFD and the analytical solution. Okay, and why? Because analytical solution is not made for when the flow is developing. Okay. And for a context here, the from CFD delta P was equal to 9.576, and which is very close. Okay, and this is the region where we are not modeling in our analytical solution, that is a nonlinear profile. Okay, so now we are getting the analytical solutions first. So we know that the shear stress formula is mu minus mu du by dr, and you know this formula exactly, that du by dr if I put the velocity profile. So I get this equation and just put the value of viscosity and every velocity and diameter. This becomes a 0.08 Pascal. Okay, this becomes a 0.08 Pascal, and this is the formula for the U, which we drive multiple times. And the delta P, I can get it from either this way, or I can get it from the wall shear stress, that we know the formula, and this value is again the same. Okay, if we take the length is 40 meter, then the same value we are getting here. Okay. Okay, now the friction factor is 64 upon Re, so F is equal to 64 upon 100 is 0.64, and the CF is actually, you can directly find out from here, CF is equal to F upon 4, this is equal to 0.64 divided by 4 is equal to 0.16, and this is the value actually we are going to compare for our CFD. Okay, so we can find out the CF by this formula as well. We know the wall shear stress, and by this formula we can also find out this value. Okay. Okay. Now the analytical velocity profile for this pipe, the pipe length is 40 meters, diameter is 1 meter, Reynolds number is 100. So if I plot this equation through the Excel, this is done in the Excel. So this is for the both sides, from 0 to the R on the top side and 0 to the R on the bottom side. So this is the velocity profile that we are going to compare with our CFD. And this is the pressure drop formulas, you know very well. So this is not a good idea to compare the analytical solution with the CFD in the entrance region, because these formulas are made for when the flow is fully developed, except the one formula that is finding out the entrance length itself. Okay, every other formula is only valid when the flow is fully developed here. Okay, so here is the entrance length formula, and mathematically it means that we discussed in the previous class that this is the partial U by partial X is equal to 0, and it means that the U is a function of only R. And we have the different formulas for the laminar flow. The formula is 0.05 into D upon Re, and typically speaking, actually we are interested in the L by D ratio. That is going to be the 0.05 into Reynolds number. Okay, so for our case, this is for the laminar flow. For turbulent flow, the formula is this one. So for our case, Reynolds number is equal to 100. So LE by D is equal to 0.05 into 100 is equal to 5 meters. So to be on safe side, actually I have selected my entrance region to be 10 meters. That's why here I have kept the 10 meters on the one side, and I made it part of the entrance region, and the 30 meters is the fully developed region. And this is true actually, okay, because these formulas are not very much accurate, so you should get some margin there. Okay, now that's why I said that the entrance region of the pipe should be 10 meters. Then the remaining length of the pipe can be any length, 10 meters, 20 meters, 30 meters, but I chose the 10 plus 30, 40 meters. Okay, and before that, this is L by D is equal to is equal to 5. Okay, so 5. So now if I take the diameter is equal to 1, then the entrance region will be equal to 1 into 5. Now this is dimensional quantity. So 5. So I made it double, 10 meters, and I added the 30 meters more. And why I added 30 meters more? Because if I increase the Reynolds number from 100 to the 200 or 300, 400, so it should be, this geometry should be able to like tackle these Reynolds number, because if you as you increase the Reynolds number, the entrance region will also increase. Okay, so maybe you want to run the other cases with some different Reynolds number, then in that case this will be much helpful. Okay, so this is what we have here. Okay, now we are going with the CFD analysis. Okay, so Reynolds number is equal to 100. I have taken the viscous density is equal to 1 kilogram per meter cube, and I have taken the velocity as a 1 meter per second. And okay, so I have taken the velocity to be equal to the 1 meter per second. Diameter is the 1 meter. So now only thing that is remaining is to find out the value of the viscosity. So put into the formula. That formula, we know that this is the rho u d upon mu. So this is 1 into 1 into 1, and around some of the 100. So the viscosity becomes the 0.01 Pascal second. This is from where we got the length, diameter, and these properties. Okay, and I'm just checking that the flow is incompressible or not. So when the flow is incompressible, when the Mach number is less than 0.3. Okay, so greater than 0.3 Mach number, flow is compressible. So if I take the Mach number is equal to 0.1, so velocity will be equal to the Mach number into speed of sound, which is 340. So it is 34 meters. 34 meter per second. So our velocity 1 meter per second is way low than the 34 meter per second. So it is like a completely incompressible flow. Okay, this is the like a proper description of the like a problem. Reynolds number is 100. We have the all the properties, and this is what we are going to be doing in this course. Okay, there are some notes from the previous class. What we are doing here. Okay. Okay, so let's go and make the geometry. Okay.